Okay, we can start. It is my pleasure to introduce Jesper Jacobsen from École Normale Supérieure. He will talk about geometrical web models. So please, Jesper.
Thank you very much, and thanks to the organizers for organizing this wonderful event, and happy birthday, Sergio. So if anybody has severe arachnophobia, this might be a good moment to go further down. So I'm going to talk about geometrical web models. It's a work done in collaboration with Augustin Lafay, who is now doing his first postdoc in Helsinki, and Azad Gainutinov, who is also seen a lot in the Paris region. So the temptation is too big to be in front of this rostrum to not comment a little bit on the coat of arms of SISSA. So as I understand it, this is Dante, of course. It's the last line of some Terzina stanza, in which he basically tells his companions that they were not born to behave like brutes, but rather to pursue virtue and knowledge. This is maybe some advice that is too little heeded these days in the world, but I think Sergio, from all I can hear, has learned these lines when he was born. Of course, now it stopped working. Of course, it's tempting to compare it to the Paris coat of arms to make a transition towards my talk. So you see there's a Z2 symmetry applied to the ship, which is now moving in the other direction. And the goal is now much more modest. Namely, the boat may rock, but at least it will not sink. So let's hope this is going to be the case. So Hubert did all the hard work yesterday of reminding you of why it's important to study conformal field theory and why these lattice models of loops are interesting. And so my work that I'm going to present is a generalization of those loop models. So you fix a lattice, nodes and links, and you place bonds, we here shown in red color, on some links, and then they will form loops, and you give a weight x per bond so that you can control the amount of bonds, and you give a geometrical weight n per loop, which is some global feature that doesn't depend on the size of the loop. And then when n is less than 2, there are going to be two critical points, a dense point and a dilute critical point, and they will be described by conformal field theories, which can take the place of Coulomb gases. And this has been discussed in the literature by all these people, Nienhaus, Di Francesco, Salers-Hubert, Duplantier-Cardi, and their ilk. And I could cite many more. So what I want to do today is to generalize these models so that you have not loops, but some more general objects, which I will call webs. And they will allow for branchings or bifurcations. And there will be certain topological rules that will give a weight to each connected component of these webs. And we want to investigate what are their properties and the possible critical behaviors. And the motivations for doing this is that in certain spin systems, if you follow domain walls, for example, in a three-state Potts model, if you have three colors, a natural domain wall is separating two different colors. But if you have three colors, you could imagine that this wall will separate to take into account the third color as well. They have also been discussed in certain network models for topological faces. And importantly for this piece of work, they have appeared in some mathematical literature in invariance theory. And I'm going to exploit this algebraic link using a paper by Kuperberg and others by Cortis, Kamnitzer, and Morrison. So here is a real spider. Now it will move forward. Okay, so here are two configurations of a three-state Potts model, and I have drawn some small neighborhoods around A and B. In the upper picture, there is a connected piece of red color that connects A and B, and there's a connected piece of blue color connected red A and B. And in between those two, there is a domain wall. This domain wall can spread out a little bit because there can be some green islands in the middle of it. But it can also be very thin because red and blue can actually be neighbor on the lattice without violating the fact that they are different colors. So I'll call this a thin domain wall. It's written also to the right of the picture a bit more schematically. On the lower half of the picture, I have another situation. There are two distinct blue clusters connecting A and B, and they cannot get quite close because if they did, they would not be distinct. But they are still, there's a foam of other colors, and blue and red can appear inside again. And this is a thick domain wall. And my original motivation for studying this kind of physics is to say something about thick and thin domain walls, and in particular their fractal dimensions. Okay, so the question is now, how do we define some good models of webs on a lattice? What are the fractal dimensions associated with it? And in mathematics, what is the right algebraic construction to account for bifurcations? So some of you might know that this loop model has an underlying quantum group symmetry, UQSL2. And one question is, can we generalize SL2 to SLN? And in particular, I shall be interested in SL3. So the first thing is now to present to you a web model based on Kuperberg's so-called A2 spider. So he has a paper with rank 2 spiders, and this is one of them. So my lattice is a honeycomb lattice. I put red bonds again, but now nodes can either be empty or they can have valence 2 or 3, meaning that I can bifurcate. And in addition, each bond is oriented. And these orientations, they are conserved at 2 valent nodes. So here's a sample picture on the lower left of the picture. So you have this closed planar trivalent bipartite graph on the lattice, and to the right, it's shown schematically just as a drawing, as an abstract graph. I'm also going to need an arrow that you see here on the left. It's pointing up. It's because I need a time direction a little later. So I need a fixed direction, which is up. About the directions, you see that directions are conserved as long as there are no bifurcations. And when I enter a bifurcations, either 3 arrows will go in or 3 will go out. So they are sources and sinks of arrows, and those alternate when I follow the graph. So it's a bipartite cubic graph. So this is all very good, but now I cannot change my page anymore. So how do you solve this? Oh. Fun. Okay. I'm going to impose now 3 rules. Formerly, with the loops, there was only 1 rule. Take a loop and replace it by the number n. Now there are 3 rules. First rule is replace a loop by the number 3 Q-deformed. The formula for Q-deformed numbers is on the bottom. Second rule, take away a tadpole with weight 2 Q-deformed. And third rule, replace a square by its resolution onto 2 diagrams. Now, if you use the Euler identity, given that these graphs are bipartite, all the faces have even degree, and using the Euler identity, you can see that there must always be a face of degree 0, 2, or 4. So it means that any diagram can be reduced to a number. And that number is, of course, very non-local, but it's the weight of my diagram. And so my web model is defined now as follows. So I give local weights, x1, x2 to up pointing and down pointing bonds, y and z to sinks and sources. I'll later take x1, x2 equal and y and z equal. And then I multiply by this non-local weight that I call wk for Kuperberg. Well, okay. I can also define a Z3 symmetric spin model, which is just obtained by placing spins that can take 3 values on the triangular lattice, which is dual to the hexagonal one. And if there's a link separating a spin j to the right and I to the left, then I'm going to associate with it a weight x sigma j minus sigma I. I'm going to normalize x0 as 1. And so then I get weights for each piece of domain wall, and they will distinguish whether spins follow each other cyclically or anti-cyclically when I go around a vertex. And it's easy to see that the partition function of this gives a global factor of 3, and it's equal to the local part of the web weight that I had before. So the two models are equivalent, provided that I can make this non-local weight equal to 1. And this I can do if I take the correct value of small q. So the q entered my q-deformed numbers. So it's this 8th root of unity. And moreover, I take y times z equals to 1 over square root 2. If I do that, and if I absorb the weights into the vertices, the 3 rules are going to look like those. And so you see, if I have weight 1 on the left-hand side, the weights on the right-hand side also sum up to 1. So it means that now it's probabilistic. And applying just this, you see that the weight of any diagram will just boil down to 1 in the end. And this is what I needed. These models can be generalized also to SLN symmetry. What I just presented is SL3, but I will gloss over that very quickly because we don't have the time. In any case, the generalized construction will give back what I just showed you for n equals to 3. But in general, this special value of q will be e to the I pi over n plus 1, and it will be equivalent to a Zn symmetric spin model. So such spin models are known to be critical when I have appropriate weights. And so we certainly expect the special points to be critical for any n, but very likely the web models have a larger critical manifold because I have parameters to vary. I can vary q, x, y, and z. And I want to find out what are the phase diagrams of these. So to investigate that criticality, well, either we need to draw up out of our hat an exact solution, which can maybe be done, or we could try to investigate this model numerically. But to investigate it numerically is more difficult than for loop models. Loop models you can simulate with all kinds of techniques, Monte Carlo, transfer matrices, this is all very well known. But when you have this bifurcation, it's not at all obvious how to apply these 3 rules. So what we need to do is to somehow transform this model into a local vertex model in the same way that a loop model can be transformed into a 6-vertex model. And then once I have this local vertex model in which the non-local weights have been distributed out locally, I can, for example, use a transfer matrix technique to compute critical properties. It's also a good starting point if I want to make a Coulomb gas construction to have a vertex model, because then it's going to be dual to a height model, and the height is precisely what you will need to have a Coulomb gas. So let's see a spider more. So how do we do this? So the basic idea is the following. So I take my bonds, the things that were read before, and I'm going to decorate them by extra degrees of freedom, which are now taking the shape of 3 different colors. 3 because it's n equals to 3. And what I want is that when I sum out those colors, that should give me back the undecorated model. So now each link can be in 7 different states because it can be empty. or it can be up pointing or down pointing with any one of 3 different colors. 2 times 3 equals 6, plus 1 equals 7. So it's going to look like this. So whenever I have a bifurcation, red, green, and blue they are going to meet. There are sinks and sources as before, and the orientations and colors are conserved when I just move along paths where I don't have any bifurcation. So let's now remind how things were done for the loop model case. So in the loop model case, what you would do to distribute out your weights is to write the loop weight as Q plus Q inverse. You would orient each loop to be either clockwise or anti-clockwise. And then you would just remark that if it's anti-clockwise, it turns 2 pi more to the left than to the right. And so you can just give a weight Q to the minus the angle turns divided by 2 pi whenever you turn left, and the game would be coming to a happy end. And it will look something like this on a hexagonal lattice. When you make turns that are 1/6 of a full turn, you get Q to the plus minus 1/6. Now, actually, in my web model, I already had orientations, and this is not the orientations that I would introduce here. So those 2 orientations, it's actually better to think of them as having 2 colors instead of the 3 colors that I had before, so that you won't get confused. So the basic idea for n equals to 3 then is to have these 3 colors. I need now to distribute out a weight of Q squared plus 1 plus Q to the minus 2 for each loop. So what I'm going to do if there is no bifurcation is that I'll take factors of Q to the plus minus 1/3 for 2 of the colors, red and green, and I will take no such factors for blue, which will then give the 1. And all of this is very nice, but then I have to say something about the bifurcations, and this is more tricky. And the solution is here on the board. It turns out that I should give some Q to the plus minus 1/6, depending on whether red, blue, and green follow each other cyclically or anti-cyclically, and also whether the arrows go in or out. And I'm going to give you a glimpse on how I derived this in a moment. But first, I have to make sure that if I sum out my colors, I get back the rules that Kuperberg told me that I needed to have. So the Diagon rule, the one with the tadpole, can be written like this. Suppose that the 2 external legs have some colors, for example, red. And then on the left-hand side, I sum over the interior colors. And I know that my bifurcations need to have these Q to the plus minus 1/6. So this I put in, and then I take out this internal structure, I sum it up, and it turns out that this indeed gives me 2 Q deformed. So that works. On the other hand, the square rule is a bit more complicated. On the left, I have to sum the internal colors of this square that I take out. And on the right, where I should have my 2 splittings, I have nothing left, but I need to sum over the 2 possible splittings. And you can check that this works as well, not only when all 4 external legs are green, but when they are in any configuration allowed by the rules. So I have what I need. So now I want to define my transfer matrix. So here is a row-to-row transfer matrix of a hexagonal lattice. It's built of small pieces that take me through just one vertex. So either I go from 2 copies of the Hilbert space into 1 copy. So 7 times 7 states into 7, or 7 into 49. And the transfer matrix is the product along a whole line, or 2 lines actually, as it were, of these local guys. So technically, T is actually going to be an intertwiner of the quantum group action, the UQSL3 that I have. So now you have to understand, or one has to understand, I have to understand what these colors are doing for us. Okay, so up pointing and down pointing. That means that either I sit in the fundamental or the dual fundamental representation of my quantum group. And the three colors basically correspond to taking a basis of this three-dimensional representation. So I take such a basis. I somehow manage to relate the basis elements as well as the identity to the colors with up and down pointing arrows, or to the empty. And then I will draw all possible transition elements in one of the small matrices that take me past just one vertex with all their weights. So it's with all their local weights. And the diagram then is supposed to now be replaced by something that will give me the smeared out version of my non-local Kuperberg weight. So let's focus on the first of those diagrams. This one, which looks like it's one of the most interesting. At this point, you need to have a book on quantum groups, because in quantum groups there are some maps going from empty to anti-symmetrize on three sides, and there is some evaluation and co-evaluation. And you need to figure out first that the diagram that we are interested in is a composition of these maps, and then you have to look up how to construct them. And then you have to write them in the basis of two copies of your Hilbert space going into one copy. So you get this 3 times 9 matrix. And if you apply your book correctly, you are going to get 6 non-zero factors of q to the plus minus 1/6. And this, of course, looks familiar because I told you that the result should be like this. So this is precisely where they were gotten from. So end of this small technical part. Somebody told me that one had to include a small proof, so this was it. So the summary is that my diagrams are actually intertwiners of this quantum group, and we can compute all the elements of the transfer matrix. And then one needs a lot of patience now to code this in the computer. And once it's done, we can start diagonalizing the transfer matrix numerically. So now there is a spider attack here again. Okay, let's turn the lattice a little bit and use this kind of geometry. So when you do a bit of conformal field theory, one of the first formulas that you come across is a formula that relates the free energy per unit area obtained from the largest eigenvalue of the transfer matrix to the effective central charge that you see on this bottom formula. So now, since our lattice is not a square lattice, there is a 2/√3 coming in, because you really need to normalize your free energy per unit area, which is not the same as per vertex. And so what we want to do is now to take lattices of, say, 2 different widths. And since there are 7 states per link, they cannot be very large. So it's going to be width 5 and 6 at most, I'm afraid. And we will then hope that the effective central charge obtained by solving the last equation for C effective and the bulk free energy F infinity at this size is sufficiently close to the central charge in the thermodynamic limit that we can see something. And this is what we see. So here I have taken just, in principle, rather random value of Q, which I take as e to the I pi over 5, just to have sort of an ugly number. And this is a color-coded plot of the central charge. Along the x-axis, you have the weight per bond, or rather its square root. Along the y-axis, you have the weight per bifurcation. And the interesting thing, well, there's a sort of trivial region to the left where the central charge is 0. This is because the correlation length is finite. On the upper right, it looks like it's minus 100, but that's a fluke. It's because the system is completely frozen, like if you had some ferroelectric order in the 6-vertex model. It's the same phenomenon. So this you should discard as well. And then you have this blue region that forms a plateau. So a two-dimensional plateau where the central charge is close to 4/5. And then you have a ridge here, almost vertically, where the central charge is close to 6/5. And so what I claim is that 4/5 and 6/5 are the exact values for this chosen value of Q. And this I will now try to explain how this can be argued. Here's first a zoom in on the interesting region where there was this ridge, and you can really see that it's very close to being constant and 1.2, which is 6/5. So that's good. So once you have this vertex model, you can easily turn it into a height mapping, because what you will do is that you will realize that when you move around on your lattice, you are actually looking at a two-dimensional height that is compactified on the root lattice of SL3, which is a triangular lattice. And so you get a one-to-one mapping between interfaces of a two-dimensional interface living on top of our two-dimensional world and the configurations on the lattice. And once you go through the math, you can find out that the coupling constant in this Coulomb gas is given by two different expressions, depending on whether we are in a dilute or a dense phase. And the central charge takes an expression true because it's two-dimensional heights, and minus some correction that has to do with G. And if you want to get gamma equals to pi/5, that like in the numerics, you have to take G equals to either 6/5 or 4/5. And by a sheer coincidence, just for this particular value of gamma, it turns out that then the central charge is either 6/5 or 4/5, confirmed by my numerics. So the Coulomb gas seems to be all right. Moreover, if now I go to the other value of gamma at which I had some special control, remember the special point when it was a Z3 spin model, then I find that the central charge will be respectively 4/5 or 0. And this is simply because then it's a three-state Potts model, and a three-state Potts model has central charge 4/5. And in the dense phase, it's like driving the Potts model to infinite temperature, the same way that an Ising model at infinite temperature would give you percolation. Here I get some three-colored percolation, and this is, of course, just independent random variables. This is going to be C equals to 0. So I am close to being done, and the time is not bad. So these web models have the nice property that they generalize the loop models to some higher symmetry. So instead of a quantum group SL2 symmetry, I get a quantum group SLN symmetry. And I focused most of the talk on the case SL3. And the geometrical content has applications to models with ZN symmetric spin interfaces. And it generalizes the well-known loop model in a very convenient way, because exactly like that loop model, it has a dense and a dilute critical point for any value of Q such that gamma is between 0 and pi. Moreover, I'm stuck. Okay. Okay. So the definition of the model, its basic properties, and this mapping to the height model, that's the object of two publications that are already out. The Coulomb gas description is written up and will reach you soon. We can also, in certain cases, say things about fractal dimensions of defects, but it's more involved than for the loop models. But in the Kuperberg paper, you will remember that I told you that this Kuperberg paper is about rank 2 spiders. So A2 or SL3, that's one algebra that's of rank 2. But there are others. There is B2, there is G2, and we can actually do other spider models for those. And they also have special relations to the 3 and even 4 state pot model. We are also planning a detailed representation theoretical study. And, well, and there was supposed to be some nice punchline in the end. Oh, I don't know how you do it. I do the same thing. And so among the further possibilities, you could try to relate this to integral models. And also about this point, we have something to say. Finally, maybe the thing that I like the most, but which I haven't done at all, is that I think it's possible to relate this somehow to SLE. So SLE, you know, is a process of Brownian motion on the real line that corresponds to having a curve that grows out of the origin in the upper half plane, and then you keep smacking down by a conformal mapping. And if you do this in a model with bifurcation, it means that your Brownian particle, sometime it will split into 2, or 2 particles will join. So it's going to give one of these reaction diffusion models that Cardi studied in the 1990s. And I would like very much to relate this more precisely to this model if it's possible. So with that, I am precisely, I think, on time. Yes. So thanks for your attention.
Okay. Questions?
So in fact, every time you say that, I have a surprise. So I am confused by the dense phase. In the normal ON case, the dense phase is the one in which you suppress the vertices, which are the 3 of them empty, right? There are
well, you don't suppress them, but you give them a small weight.
Small enough to be in the dense phase.
Yes.
And the attraction point is
so what happens in the loop model is, suppose you start from bond fugacity 0. Suppose you keep increasing it. At some point, the largest loop will have its size diverging, or it will be of the size of the lattice. When this happens, precisely then you hit the critical point of the dilute phase. If you increase just a little bit more, then you are going to flow into this dense phase in which the combined fractal dimension of all loops is equal to 2. And then there's going to be something exceptional happening when the bond fugacity is strictly equal to infinity. Then you get a fully packed loop model, which by some kind of chance also see its symmetry enhanced from SL2 to SL3. But was that a question?
And there is something, so there is a good analogy of dense dilute between rank 2 and rank 1, or it is just a name that is mutuated, but the mechanism is a bit different?
It's the same phenomenon here. So of course, now I have 2 kinds of ways of covering my lattice more. Either I could ask for having more bonds, or I could ask to have more bifurcation. So this is why my diagrams were in 2 dimensions with the color-coded contour plot. Okay, now if somehow, if you just manage to tune at least one of the 2 parameters so that you get enough material on your lattice, then you will be on this big plateau where the precise value doesn't matter. And this will be this light blue plateau, and it will correspond to the dense phase. So then both deviations with respect to the exact critical point are irrelevant. Or alternatively, you tune one with respect to the other, and then you get a 1-dimensional submanifold, which is this ridge And this is the analog of my dilute critical point. So it means either tune 0 or 1 parameter to get a dilute or a dense point.
And does this generalization to SL3 depend on the trivalent nature of the hexagonal lattice? So if you generalize to other n, will it have to be on other lattices?
So all of this works well when it's a cubic lattice. And the reason that we chose this specific lattice was in order to get a model that resembled as close as ever possible to the nicest version of the loop model that exists, which is the one on the hexagonal lattice. However, it's quite possible that you could generalize to other loop model, other lattices, but our secret hope, which is now realized in unpublished work, is that there's an integrable model sitting behind this, and indeed there is, and this is presumably best attained when taking the simplest lattice. So from that point of view, I think we took the right strategy.
And just out of curiosity, why do you have to write U minus Q instead of UQ?
This is purely technical.
Okay, thanks.
It just makes certain formulas look nicer, but unfortunately, just this one specification of the subscript of UQ then looks strange enough that you would ask your question. That's life.
Okay, if there are no more questions, I propose to thank again Professor Jacobsen